to not interrupt Brian. I'm not sure what his poll plan is, but I'm sure there'll be some time for Q&A towards the end. With that, Brian, I'll stop sharing my screen, and when we're ready, Scott, we can get started.
Okay. Thank you, John. And let me share my screen here. Stand by. Okay. I'll see my screen.
Yes.
Okay, great. Okay, so about to present on advanced thermal management. And let's see, there we go. A little about what we're going to be covering today during this session is effectively heat management. So managing heat in your enclosures. So for those of you who are building your enclosures or modifying enclosures, you're concerned about heat buildup inside of those enclosures due to climate, or you're considering adding ventilation, or you're just considering new designs. These are some things just to kind of broaden your understanding of heat management with our hobby in mind. So a lot of this kind of covers a very broad spectrum, but I've kind of narrowed it down to just the elements that are pertinent to those of us who are building enclosures or managing things specific to our hobby. So to that end, looking to design in airflow. So there's a lot of different approaches to cooling. We'll talk about some of that, but primarily with airflow kind of designed cooling and implementations. And then as we kind of walk through just cooling in general, I want to also introduce a new plugin for FPP called the Advanced Thermal Management plugin, and some of its capabilities that will be available once it is complete. First, a little about me. I've been doing animated light shows for about 7 years now. This will be my 7th year this year. Started doing pixels at the very beginning, so never really had a traditional show per se, but have always used Falcon products, controllers, with X-Lights and FPP. So I use FPP for pretty much everything, including off-season, landscape lighting. We use it for powering some or driving some of the lights inside the house. I've got some stuff in my daughter's bedroom that we use with FPP. So kind of dyed-in-the-wool FPP power user, I guess you could say. Other things I like to do, in addition to kind of dealing with light stuff, is home automation. I do a lot of home automation stuff, inclusive of FPP. So FPP is integrated with our home automation as well, and travel. I do a lot of travel for work for just by necessity, but I also like doing it for fun. So it's a little silly when people hear that, but I do. I like kind of view them in a different way. And just something fun. Some people don't know about this. Some people do. I was participated in a program called the Net Cafe that PBS had aired in the late 90s, early aughts, on an episode about one of the projects I was working on at the time called, with a wearable computer. So if you're going back to the Internet Archives, you can find me in that. Okay, I want to set the stage initially by describing some of the concepts that you need to at least be aware of when just considering the aspects of thermal management. So from the top, equipment operating temperature range. We'll get into each one of these as we go. This is more of a table of contents than anything. Efficiency profile is kind of a fitting in with the temperature range. The ambient temperature range, delta T, condensation in the dew point, cooling methodologies, and airflow. So we're not going to get into any real kind of math here. This is more just talking about the concepts used. If you want to actually get into the computational aspects of this and actually using, if you're familiar with it, a CFD modeling tool for modeling airflow, have at it. I'm trying to keep this as generally available as possible without going crazy technical. But there's a lot of tools out there that if you want to go deep, you can go deep. And for those just reading the context here in the slide, CFD or computational fluid dynamics is essentially how you model airflow in systems. So there's a lot of cool tools that are out there for doing that if you're designing enclosures for different stuff. In my day job, that's part of what we use for modeling airflow through some of our cabinets that we have displays in. So things like that are commonly used. Let's first start by kind of describing the basics of equipment operating temperature range. So when you're talking about a system, it's made up of multiple different parts. And when you're trying to put multiple different parts into an enclosure, say a controller, say maybe a BeagleBone or Raspberry Pi and a power supply, you have to look at all of those as an aggregate of kind of the made up system. So when you're looking at operating temperature ranges, you have to look at all the pieces. You can't just find the ones that run to the highest to the lowest range. You have to look at them all. So the context here is if you're looking at it, something like that, you may be limited with the operating temperature range on your devices. Typically, electronics devices, and this is not always true, but it's more common than not, operate between basically just above freezing to 140 degrees Fahrenheit and Fahrenheit, and then 0 degrees to 60 degrees centigrade. But there are components that either don't work as well above certain ranges or don't work at all. Some don't work below freezing. Some do work below freezing, but you have to consider the ones that don't and kind of consider that in your design. Usually each component, all included, the things that we use in our hobby, have a rated temperature profile in them. And there's things that you need to do to consider both the low end and the high end that it's going to be operating in. In the same respect, some devices at least, may have different behavior as they're operating in different temperature ranges. So, and I used as an example here, a common power supply that we often use for our stuff, the Meanwell LRS 350s line. This is inclusive of all the voltages that supports. In the case here that's shown, this particular device actually for 220 does roll off in terms of overall efficiency. So if you're looking at, okay, it maxes out at 29 amps, well, that's only 29 amps if it's operating at 100% efficiency. If it's not, it's going to be derated. So you have to actually derate the maximum high-end rating of a device as it's above the operating temperature. So it basically says, per the graph there, that at 55 degrees, it starts rolling off up down to about 80% after it hits essentially between 50 and 70. 70 is basically the maximum operating temperature for that, centigrade, that is. Now, there are other devices that may also operate, but they may operate less efficiently. And why that's important is if you're pushing things kind of at the top end of where you would be, what their ratings are, you may find that they consume more power because a lot of things don't operate as efficiency as they're hotter. So one of the reasons that you want to consider cooling in some cases is, for one, power. You're going to be potentially drawing a lot more power if it's hotter. You drop it down to a lower temperature, it's going to be more efficient, and you've got that power available for using in the rest of your system. So typically people don't usually push it all the way to the very hairy edge of where your limits are. But if those of you who do, I know some of you do, this is something just to take a look at and consider, that there are some of those limits that may come into mind if you're worried about, why is my power supply cutting out? Why am I seeing voltage drop in these conditions? There may be reasons apart from the actual specification of the hardware itself. It may just be the operating environment it's in based on temperature. Another one here, ambient temperature range. So, and this varies a lot for the season that we run, or seasons that we run our devices, particularly if you're in the northern or southern hemisphere. This can be pretty significantly different. And that's the kind of thing you need to understand. So if you're only going to be operating your display during Christmas, you don't do any other shows in any other seasons, you operate in the northern hemisphere, it's typically going to be a little bit on the cooler side. You may well be within a safe operating range that you don't necessarily need to use secondary cooling. It may just be the ambient is enough to keep it low. But if you're in the southern hemisphere, you're in the midst of summer. So obviously, in that case, your ambient's going to be a lot higher, and you potentially are going to be more concerned in that case about operating. You also, again, looking at if you are doing like multiple seasons, so those of us who do maybe a show for 4th of July, maybe you do another one for Christmas, those are very different temperature ranges. So you may, in the case of 4th of July, or if you're doing an October show and parts of the latitude where it's still fairly warm at that time of year, you may still need some cooling where you wouldn't necessarily need it for your Christmas display. So things to consider is that it may be necessary to operate differently depending on those times of year, depending on the season, based on that ambient temperature range. Let's see, here we go. Yeah, and I guess the other thing to consider too is that all of these systems are considering that, at least that we're going to discuss today, we're not talking about artificial cooling. So we're not talking about like refrigeration systems or anything like that. Those exist for larger cabinetry and things that typically are not used in our hobby, but they're out there for certain other systems. This is really going to be focusing primarily on some other methods of cooling, either forced air or natural convection, but not introducing kind of a lower temperature threshold than what the ambient is. And this comment basically is describing that if the ambient temperature is lower than what your target temperature is, or where you want to lower your equipment to, there's no way that's going to happen, because you're introducing that ambient into your environment, into your enclosure, to attempt to cool it. So clearly, if it's higher, it's only going to raise the temperature. If it's the same, it would maintain. So just be smart with where you want to look to run. Another concept here is delta T. So this is something anybody who's dealt with refrigeration systems or HVAC, this should look a little bit more familiar terminology wise to what you've seen before. So it basically, in the context of cooling specifically here, it can be used in other ways as well, just within general use of physics. It's the temperature change across the system. So basically what you're going to be lowering the temperature to from what it would be if it weren't being cooled. Basically, discussing here is with fresh ambient air. So assuming, again, forced air cooling, bringing air in from the outside to use that as cooling, basically forcing that air through the system to drop the inside temperature of your devices. This is basically what's going to happen. It's going to drop that temperature from some amount. The assumption being is if it's actually cooling, this will occur. The larger the difference between the ambient temperature and the system temperature, the less airflow that'll be required to cool the system, because that just makes sense, but you can see the math on that as well if you want. But it basically means that if you have a higher differential between your inside temperature, let's say you're referencing, say, a 40 degrees centigrade reference temperature, and you want to try to drop it a little bit, or maybe 50 degrees is a good number. And your ambient is, let's say, 30. Still pretty warm, but it's much cooler than what you want to reach in terms of your target temperature. So you definitely be able to cool in that case with ambient. In most cases, you're going to be operating from a much lower ambient temperature. So the bigger differential is really what matters there. So you don't need to push quite as much air to get the same cooling effect. And condensation. So this is something that a lot of people take for granted, particularly if you're operating where it's much cooler outside. Say, for example, during the Christmas holiday, if you're in a latitude where it does snow, and you need to worry about introducing hot, moist air in contact with things that are cooler, basically below where the dew point is. The effect basically being is that if you're drawing that warm air over something cool, you're going to start seeing condensation. And if you've ever been, say, for example, in a place that's modestly humid, you're wearing sunglasses inside, you walk outside, all of a sudden your glasses fog up immediately as soon as you walk outside. Why is that? Your glasses and the hot outside air have effectively reached the dew point on the surface of your glasses. So they're starting to collect the moisture that's in the air, and it collects on your glasses. The very same thing can happen to the interior of your enclosure. So if you've got anything above 0% humidity, and you have hot air, which would be introduced by your power supplies, your enclosures, they're warm, the outside air is very cold. If that comes into contact with some of that cold surfaces, you may see condensation form there. So things to think about is what's happening with your airflow in those cases. If you do have a potential for condensation, do you have a place for it to go? Or is it going to pool in the bottom of your enclosure and cause it to basically get really full? There's situations where people have sent pictures and they said, it hasn't rained, why is my enclosure full of water? Well, this may be a reason. So just take that into consideration when you think about your design. There are good workarounds to maintain a higher interior temperature in that case. Maybe you don't want to use forced air to cool, but you might want to increase the ambient or increase the temperature inside your enclosure because it is so cold and you don't want to have to worry about this. You might need to put a heating element inside your enclosure so that it stays warm enough, because the enclosure and its contents may not be generating enough heat to maintain that temperature. So just things to think about. Look at the curve in terms of where the dew point is, where your operating temperature range is, as well as your humidity. If you're operating at 0% humidity, there's no moisture in there at all, but very few places have a consistently 0% humidity. So just something to look at for each and every situation. All right, so common cooling methodologies that we use in our hobby, there are others, but we're just going to talk about the 4 here, and some of these are more common than others. So heat sinks basically typically are only used to move heat from a smaller surface area to increase the surface area or the surface area so that the heat's easier to move away. Say, for example, you've got a PC, it's going to have at least minimally a heat sink inside, usually a heat sink and a fan, because the heat sink, all it does is move it from the surface of the actual die of the CPU and other components like the VRM and memory that are hot, and increases the surface area so it's easier to move that heat away by drawing air across it, or just natural convection alone, which is the next item here. So convective air cooling. So basically this uses natural convection, which naturally makes hot air rise, but it needs somewhere for it to go, and it also needs replacement air. So heat will rise if there is a place for it to be replaced by. So naturally it's going to have an air current that would draw it up naturally, but it needs to have something to replace it with. So what that means is you need a place for fresh air to come into the system, and you need a place for exhaust air to leave the system. In all these cases, that's going to be the case. Forced air cooling basically takes that a step further, where it uses a fan or something of that ilk to be able to push air through the system. And typically that'll allow you to work in systems where you can't only use convection to carry your heat away. You may have flow restriction based on the design of your enclosure. You have to push air a little bit further through, or you get hot spots where convection alone doesn't work. More often than not, convective air cooling doesn't work well enough to move enough heat away quickly. So we likely will have to use forced air heat if you're using things that generate a much higher temperature. Say you've got 2 or 3 or 4 or 8 or 10 power supplies in the enclosure, that's a lot of heat you got to deal with. So it's got to go somewhere. Another one that people aren't really using much yet, but this is commonly used in other systems, is heat pipes. And basically what they do is they typically have a phase change medium. Phase change basically means it changes from heat or from a vapor, a gas basically, into a liquid and back as part of how it moves the temperature or the heat from one side of the heat pipe to another. Typically heat pipes are used in concert with a heat sink, maybe with forced air cooling as well. If you look at a lot of modern PC designs, primarily for the CPU cooler, they'll use a combination of heat pipes and forced air cooling and heat sinks to be able to move the heat away. Usually they use the heat pump or the heat pipes directly on the surface of the CPU die. They curve around, then they come into contact with a large copper heat sink with a fan mounted in it. And the idea with that is that the heat pumps or the heat pipes very quickly move the heat from one side to the other. And then the heat sink actually is enough of a good area, a surface area for the fan to be able to draw that hot air away. If you were just to use the fan on the heat pipes themselves, it's not enough surface area for them to be effectively cooled. So in something like that, they could use a combination. Conceivably, even in our hobby, we could use a similar approach to use heat pipes to move heat from inside the enclosure to outside the enclosure. But of course, you'd need to maintain waterproofness of whatever system would be using that. But it's something that maybe in the future we'd be able to use more readily. It's just not something a lot of people use yet. Another one, airflow. So we talked about kind of forced air cooling. Typically, folks will use fans for that, either a kind of a radial fan, PC style fan, or what they call kind of a snail fan to push air through the system. Typically, folks use PC fans because they're cheap, they're readily available, they operate in the voltages that we run with, so they're more often used than not. Typically, a rating that you'll see on any PC fan or its ilk is going to have 2 different things. One, it's going to have a max static pressure rating. It basically says how much force will this fan have to push air away? So if you're pushing air into an enclosure, if you've got a lot of flow resistance in there, so it's really densely packed, you've got a lot of components in there, you got a lot of wire in there, there's not a whole lot of open space to push air through, you're going to need a higher static pressure rating on your fan to be able to push that air through. Otherwise, the fan is going to run, but it's not going to move any air. Another factor is the max airflow. So it's typically going to be a CFM or a cubic meters per hour. Rating basically gives you an indication of how much actual airflow is pushed through the system. Typically, this is more of a function of the size of the fan, the surface area of the fan. So the bigger the fan, usually more airflow. This often, just for consideration's sake, if you're building a smaller enclosure, you're not going to be able to use a larger fan to be able to move the heat away because you don't have the space. A larger fan is much easier to do that with because you've got that bigger surface area. You can push a lot more air. You may, as a kind of accomplish the same goal, need to rotate more on a smaller fan to push the same amount of air. Typically, the higher rotation speed also equates to more sound, more fan noise effectively for that use of the fan. But you'll see, at least functionally, these are the two critical settings. That obviously the actual noise rating of the fan is also something that they typically will provide for PC fans. I didn't list it here, but that's another rating just to consider. There are some fans that do a better job of being lower noise, moving the same amount of air, have the same amount of static pressure. Typically, those fans tend to be on a little bit more of the expensive side as opposed to your run-of-the-mill fan. Your Noctuas and the like, they typically are designed for that purpose, but their price is higher. So just bearing in mind kind of what's critical for you. If you're operating outside, something like fan noise isn't a consideration that you'd have to worry about, but the static pressure and the airflow certainly are. All right, so we've talked about some of the concepts that go into the things you need to worry about. What does it actually mean? I've kind of distilled this down to a couple of bullet points. And in the course of our presentation here, I've tried to keep within the time allotted. So we can't go into a huge amount of depth to explain and justify each one of these, but these are essentially kind of a best practices list when you're designing an enclosure. First option or first bullet point here is ensuring that the size of the fresh air intake vent is equal to or slightly larger than the size of the hot air. The reason why you might want it slightly larger is it's generally a good idea to design a slightly positive airflow through the system. That prevents you from drawing in air from other portions, potentially maybe inadvertently drawing it in through a cable vent or something, as opposed to trying to draw it in or out through a particular fan vent. That's just a general enclosure design consideration that's often used. Another one is, again, most of our enclosures are outdoors, so you want to prevent water ingress. The easiest way to do that is use a vent cover, and they're cheap and relatively easy to find. This one listed here is for bud enclosures. They make two different sizes of these. They're really easy to do. When I first got started, I started making my own because I didn't know about these yet. It was a big pain to make your own doing that, but now you can just buy off the shelf units. You can mount a fan behind it or not. They're really easy to do. Just drill the hole, slap them in, and you're done. They're sealed. They work really well. But those will prevent water from getting sucked in into your enclosure inadvertently. If you have a very high positive airflow, you may be drawing a lot of other things in there that you may not want. So similarly, with the water ingress, you want to worry about filters. And if you don't do that, you might end up with dust, you might end up with bugs, you might end up with all kinds of other stuff in the enclosure that you don't want. So as a general practice, it's always good to try to seal up and use filters where you can, because otherwise you're going to end up with unexpected things in there. You can use readily made fan filters that you can buy. They're for PC fans. You can get ones that are either pre-made to size or cut to size. They come in a sheet. You basically use a pair of scissors. You cut them out to whatever you need. Depending on the use case, you can either get the ones that have a little frame in them that they basically contain the filter in. You put a screw through four corners on it. You have a little snap on top, and it encloses the filter in it. And then if you need to, you can pop it out and then vacuum it out in the off season to clean out anything that it's sucked up that hasn't gone into your enclosure. Other ones, take advantage of natural convection. Exhaust hot air at the top and take fresh air in at the bottom. Some people just stick it wherever they want. Yes, you can do that, but it takes more energy to be able to push that air from the lower part of the enclosure back up, or push that hot air out, because convection is going to naturally want to have that hot air rest at the top of the enclosure. You can take advantage of that so that you don't need to design in as much, essentially how much current is going to be going through your fan to push that air. So if you can, do it that way. Another one, offset. So the reason for that is if you have inline input and output, is that it will basically find the easiest path to push air through your enclosure. If you offset it, you want to introduce turbulent airflow. The reason for that is it'll mix the air around inside your enclosure to remove more of that static hot air that would otherwise be trapped in your enclosure. If you look at, say, for example, a design for a server power supply or a server rack mount PC, they're designed with special vents and special fins in them that direct airflow through the enclosure in a particular way. Typically, they're going to drive it over the surface areas they want to cool and then right back out again. Those are typically designed specifically for that purpose. But unless you're doing that with your enclosure, and many of us don't, nor do we really need to, you just want to make sure the air mixes around in there and it takes away whatever it picks up as it mixes around. Easiest way to do that is to just introduce turbulent airflow. And as I mentioned before, cold surfaces can be the source of condensation. You may think you're completely sealed up, even though you're introducing air. If you're operating in a cold temperature with anything other than 0% humidity, you might pick up condensation. So think about that's going to happen. If you might get it, give it a way out, i.e. weep vents or weep holes. Give it a way to collect. You might want to put in one of those air dryer desiccant pots inside if you have a space. That'll collect air, moist air or water if it starts building up inside your enclosure. Best thing to do is try to design it so it doesn't happen, but there are counters for it if it does. Okay, bit of a topic change. So we've kind of gone through the basics of the just dealing with hot air in a system. And the next part is to walk through a little about kind of the in development plugin for FPP called Advanced Thermal Management, same name of the presentation. I'll be able to give you a little bit of an intro to what this looks like. I can give you a quick demo. It's not as of yet completely finished, but there's bits and parts that are, and I can kind of show you what that looks like. So the kinds of cases where you would want to use that sort of thing, we'll get to in just a minute. Primarily, what the problem this is trying to solve is right now we've got a lot of need in certain cases. If you're operating at a temperature where you need to reduce the operating temperature inside an enclosure, people are going to want to use fans. The existing implementations for a lot of that are relatively simple, and we'll kind of explain that in a little bit. But the purpose for the Advanced Thermal Management plugin is that it'll allow you either with a Raspberry Pi natively with a hardware PWM, or an IC made by Maxim called the Max 31760. And we'll kind of explain what each of those use cases are. So specifically, if you've got, say, a Falcon controller or any other number of controllers that actually has a pin, 3 or 4 pin fan connector on it, typically what those allow you to do is you set a temperature threshold after which the fan will turn on. They typically will go from 0 to 100. They don't really allow you to alter the fan speed of the fan directly with those. They basically, if it reaches that temperature, turn on the fan. Once it drops below that temperature, it'll shut off the fan. And in many cases, that may be perfectly fine. You may not worry about it. But say, for example, if you want it to behave differently and you've got different uses, you're going to be operating it during the summer and the winter, you may not want that fan coming on at all at certain times of year. Natively, you'd have to go in and adjust those settings if you don't want it to come on. Basically increasing the temperature threshold so that it effectively doesn't come on, or disabling it entirely. Or if you want to worry about noise, say, for example, if you've got things indoors. I've got one in my daughter's bedroom that's right inside of her bed. It's actually built into her bed that controls lights that are in her bedroom. I've got another one that we put under our Christmas tree that controls our indoor Christmas tree. Well, our outside show is running as well, both of which are sensitive to both temperature. We need to manage the temperature, but also noise. So you don't necessarily want to run the fan at 100% if you don't need to. So this will help address that concern. It also works in the case where you might need to control more than one fan, and if you want to know what the actual fan speed is or if a failure has occurred. And most of the current implementations don't do that. They don't tell you if the fan stopped rotating. They don't tell you if you've exceeded your target temperature or anything like that. And this plugin will provide for that. First and foremost is the Pi. So with the Raspberry Pi, you have effectively 4 pins or 2 hardware PWM controlled sets of GPIOs that you can use to control fans. That's basically in a case where you're not using pixel strings, because if you are driving pixel strings directly off the GPIOs with a Pi, you can't do them both at the same time, because once that feature is enabled, it uses both of the 2 ports to control pixels, and you wouldn't be able to use the Pi PWMs for that purpose. But if you're using an external controller that's using E131, or have a Pi as kind of a larger setup where there's others that make up the system. You may have a Culp controller doing your main show. You may have a Pi in another place. You could use the Pi for this. This method of control is best suited for 4-wire PWM type fans. You can do it with 3-pin fans or 3-wire fans, but you're going to have to make sure there's some extra protection if you're driving directly from those GPIOs to the fan. Primarily, the way that's done is with a circuit like shown on the screen here. You're basically toggling it on and off very quickly. And you see the L1 is actually the windings of your fan, and they have a diode in there to prevent basically any stored energy that's in that coil when it's running as it's shutting off from getting dumped back into your system by means of what's called a flyback diode or a shunting diode. Basically, that dumps the current back into the coil so it doesn't go into your system. But there's some parts you have to add to make it do that. That's why I'm saying with a 4-pin fan, you don't need any of that. You plug it straight into your GPIO. It's already logic level buffered for the control. You don't need any extra bits in there. The only downside with the implementation, at least right now with the Pi PWM implementation, is it doesn't support the tachometer feedback. There will be a way to do that eventually, but natively as it is right now, there isn't a way to support it. Primarily, that's because the operating voltage could vary between that's supported natively on the Pi. The Pi operates at 3.3 volts. Fans operate either at 5 or 12 or some other voltage. So we'd need to be able to convert that voltage into the logic level that's used by the Pi safely to be able to do that. So we'll have to have at least one piece of hardware in there to buffer that to safely be able to read the state from the fan. The next one is the Max 31760. So this is a bit of a more advanced approach to doing the same thing. It gives you a lot more control than you would otherwise be able to do from any other type of fan controller. It can operate either independently, completely independently. You basically program the device and just give it power, and it'll run your fans based on a reference temperature, either on the device or externally, without any other control. Or you can interface it with a Raspberry Pi or a BeagleBone via I2C. And then they can manage it, and they can also use it with the plugin to be able to do stuff like sending alerts, generating SNMP statistics for your fans, etc. It can also support 2, 3, and 4-wire fans. So pretty much any type of fan you can come up with, any operating voltage, they're designed to be able to do that. They support 2 separate tachometer inputs. You could have 2 independent fans. They're controlled by a common PWM controller for it. But each fan is independently monitored. So they know if they're spinning up correctly, if they've failed, stop rotating, they'd be able to detect that. They do support both a built-in temperature sensor that's on the actual IC and an external temperature sensor, which is either a diode or a transistor. All right. Some other things just in terms of current state. Where are we? Right now, I've got bits and parts of it, and I'm going to give you a little demo here, and we can kind of show you what it's doing so far. So right now, kind of the low-level stuff is done. Some of the front end is done. Still needs some testing once it's at a state where it's ready to go. But let me show you, where are we? There we are. A little of what you can do with it. So generally speaking, we're going to get into the Pi PWM. This is kind of the settings that you'd be able to adjust in here. So basically the GPIO pin that you'd be able to pick, these are the hardware PWM pins. So it's going to restrict you to those for now. We don't currently support software PWM with the current version of Pi. And the temperature set point that you'd want to set as the kind of the target threshold. And the reason and what that means is it's essentially using a PID loop to control that. So it's a control algorithm that basically targets that temperature not to exceed. So as it approaches that temperature, it'll increase the duty cycle or the on time effectively of your fan. So it would cool things down before it reaches that temperature. And as you actually reach the point where it does, let me show you one of these guys when it is actually running from running season. Let's look at that. So you can see here, it's trying to maintain a temperature that's just a little bit lower. These are days where it got really cold. There's not a whole lot of resolution to these graphs because it was a couple months ago, but for reference, this is what it was. There's a couple days there, it got really hot and it overshot the temperature by a little bit, but for the most part, it was able to maintain that temperature and keep it under. But the idea is that it will try to not run the fan if it doesn't need to. If it's cooler than that, it'll basically drop that duty cycle down correspondingly. What you can do with that is you can set a minimum fan speed. And typically what you would need to do for some fans is that they don't turn on below a certain duty cycle. If you send them something less than that, it will automatically either turn off or set themselves internally to a minimum RPM, basically, because they won't be able to start up unless they're at a temperature or a duty cycle above a certain number. So for something like this, you could set that minimum number. 10 is usually a good number to set. You set it any lower than that, then if you're attempting to send it to 1, 2, 3, 4, 5, 6, 7, 8, your fan may not actually start. So this lets you set kind of that minimum threshold. You can also set up to basically turn it off below a certain threshold, completely off. So it won't even attempt to turn on until it hits that minimum fan speed. So these two together can be used in concert. There's some logging that you can look at. There's some other internal stuff for verbose temperature threshold. This is primarily used for the S&MP reporting in here. So you can actually see stuff like this and look at kind of runtime over time. Going over to the max 31760, we've got a couple of different things we can set. You can pick the device address. The device can be at 1 of 10 addresses. Conceivably, you could support up to 10 of these devices concurrently, plus Pi PWM. I can't imagine anyone would want to do that, but it will allow you to do that. This particular device is only one connected right now, so it's telling us it's at the default address of hex address 50. So lots of settings here, and we're taking full advantage of the built-in tooltip information that's available in FPP. And note also that this user interface, this is using the 5.0 version of FPP that Adam spoke about earlier. So it might look a little different than you'd seen before if you didn't see Adam's presentation, but this is all based on FPP 5.0x. So again, tooltips, these will tell you a little bit more about what you're seeing. Some of these tooltips I need to add some more text to, but the intent basically is that we'll give you a little bit of information about this, so you don't necessarily need to go back and reference the documentation. Some of these are going to be options that would only be available for developers. I've kind of got it set up so you can see everything right now, but for the most part, anything that has these indicators on there, you wouldn't necessarily ever need to fiddle with. What I'm intending to do is put a wizard in here so that when you can click on a button, you basically say, I've got a 4-wire fan. I want to use this threshold, set my temperature curve, and just it will automatically populate all the values for you for it. If you have 1 or 2 fans, it'll basically ask you some questions and then set all those values for you. If you then want to go back and change them, you can, but without having to manually go and fiddle around with each one of these, the wizard will help kind of put some of that standard stuff in place for safe values, depending on what kind of use case you have. Other things in here, the temperature index source, like I mentioned, you can use either the built-in temperature sensor, the remote temperature sensor, which can be connected at a distance from the actual device, or a max of both. So you can have a temperature sensor in one side of the enclosure, another one on the other side, or top and bottom. You can use the maximum of both. It allows you to do that with the device. You can also assign alert masks. So if you want it to tell you when some of these things happen, you can disable TAC2. So say, for example, you've only got 1 fan enabled. or one fan attached. You don't necessarily want to get the tach alarm in the case for fan number 2 because it's not plugged in. So you can turn that off. You can also, if you need to, you can turn off some of these other overtemp, remote overtemp, local overtemp as you need to, because you may have a use case where you need to do that. This allows you to. You can also set some other thresholds in here, essentially what you want it to do. Say, for example, spin up. This is basically tells you what it needs to do. Once it actually gets the fan up, it typically, when you set this, it sets the fan to 100% until the fan's actually ramped up to a point where you've set the minimum threshold for the tachometer reporting back, and then it would drop down to your target RPM. So it would ramp up fast, it would be a little louder, but it would guarantee that you're able to reach the target RPM for the tachometer. So in some cases, you may want this off. In some cases, you may want it off or on. The fan fault mode, some of these other modes, these are more internal functions. You can actually have it drive an LED indicator. And one of the pieces of hardware that is used for this that I'm prototyping with here in this example is called the fan to click. They have a little indicator LED on here, and depending on future hardware implementations that use this, they may choose to do this on a buzzer or another external LED. Not really clear yet, but this would basically uses one of the IOs directly on the Max 31760 to do that. All right. Let's see, get back to here. There we go. All right. So another thing too, the device has RAM and storage locally on it, an E² PROM. So you could read and write the settings directly off of that in and out of FPP. So FPP is really just controlling it, reading the settings off the device, setting the settings into the RAM, and then potentially writing them into the EEPROM to keep them permanently on the device, or as permanently until you replace it. But this is basically operating with the settings on the device independently with FPP separately. So we also have the lookup table. So this is essentially how the device independently controls it. It gives you a temperature range and where the actual RPM is going to be set to. Basically, it allows you to set a different duty cycle for each one of those temperature ranges. So you might want it to be, when it's super cold, you might want it off. If it warms up to a certain point, you might want it on. You can actually handcraft these if you want to tweak them. The intent with this is using the wizard, it'll give you a target temperature, and then it'll automatically build you a RPM curve or a duty cycle curve to match to your target temperature. But you could also go back and fiddle with these as you want. That is pretty much it for this. I guess another thing I just wanted to show, because I kind of whizzed by this, one of the other features that's going to come alongside with this is the device will allow you to be able to export your fan information and temperature information SNMP. So if you have something like a monitor program, you've got an NMS, you might have another tool that you want to use. This happens to be Cacti that I'm using here. It'll show you some of this stuff, your target temperature, your set point, your actual temperature range, so that you'll know if you're exceeding your temperature. Say, for example, I've manually turned my fan on in November, so it's been on in this range. But during the summertime, you see it's getting up there and it's regulating. Some of the time it's dropping down a little bit, but it's mostly regulating. But if you could see over time, maybe all of a sudden something happened. Maybe you had something break loose inside your enclosure and jam your fan. You could see when that happened. In addition to the plugin telling you that you had a fan, it had stopped turning because it's going to get an RPM fault, and you would exceed your temperature, so you get a fault on that as well. But you could see historically when that happened if you were monitoring the device. You could also look at the actual duty cycle. So, for example, this particular device, up until end of last year, it had basically been operating at its minimum RPM, but at that time, it was going up and running at a higher duty cycle throughout the course of the day to manage its temperature to keep it under the regulated temperature. Let's see, anything else? Those are the primaries, I guess. Another one, I guess you want to take a look at, again, just code that is going to be going into the plugin primarily for the the Pi PWM stuff. I wrote this a couple of years ago for the same purpose. Wasn't a plugin. It's basically the same functional control code. I'm rolling this into the plugin to be able to use the same features and functionality. If you want to look at that, you can. But that's essentially the genesis of where a lot of that came from. Let's see. I think we are at 18 minutes past. Give a little time for questions. I've kind of gone through a bunch of different things, and obviously there's a lot of different material, both from the design of the enclosures as well as the plugin. Let's get into some of the questions. I'm going to go back here a little bit. Damien's listing in chat. I'm going to go from most recent to oldest here, but yes, 31760. There is a fan to clipboard. That's what I'm using in the picture shown. Any thoughts on an enclosure for a projector outside where there is no shortage of winds and the temperatures can go over the month can vary? So something like this, I'd recommend using the Max 31760 for it, because you could set a temperature where you don't want it to turn on. That's a pretty low temperature to operate in. You may not want it to have it running at all there, or may want to force it to be off. Obviously, there may be cases where you would want it to. You might need a heater in that case as well. That's going to be a kind of above and beyond this. If you need to maintain that temperature with the actual projector off. If the projector is on, it's going to be generating its own heat. So you probably don't need to worry about that too much. Let's see, positive air. Putting fans in an enclosure, should I use the fans as an exhaust fan so the air pressure and therefore the temperature is a little lower than the enclosure? Does it not matter? It depends on the fan. So this is where the static pressure rating kind of comes in. That's how much air it's pushing. If it has nothing to pull, as in there's too much flow resistance, it's not going to move any air. You can see that. My general practice on this is I use fans to draw air out, and I use a filtered fan vent cover on the inlet. That way it's easier to service it, because if you otherwise put the vent and the filter before the fan, you have to disassemble the fan in order to access the actual material, the filter material. So in some cases you have to combine them together, but as a general practice, I prefer keeping them as the pushing fan basically, or pulling fan, and then leaving the vent filtered from there. Any other questions? And we could probably unmute folks as well.
Yeah, if anybody has any questions, please go ahead and unmute yourself.
Okay. If you have any questions or something comes to mind, obviously there's a big dump of information, a lot to digest at once, and it kind of is the assumption is you're going to take this off and go do your own research and kind of figure out what you need for your specific use cases. Feel free to reach out. I'm on the Facebook group for FPP, more so than I am on the forum. I don't spend as much time on the forum nowadays, but I am on the Facebook group quite a bit. If anything comes up, and you can reach out to me directly as well. You can see that from the link for, if you want to, you can take a look at the Advanced Thermal Management repo on GitHub. It's kind of showing development where it is. If you want to play with it, you're welcome to do that. And it's also got contact information on there as well. A couple more posts in chat. Somebody says they have an ESP01 and ESP Home to manage fans temperature in your boxes, using it with Home Assistant. Yes. So you could do that as well. I mean, ESP01, if you have open GPIOs in that, you can do that as well separately from this. But you could potentially use one of the available GPIOs on the ESP for that. All right.
Well, great. So Brian, I just really wanted to say thank you for taking the time and putting this together. It was very informative. It actually kind of gave myself some ideas for next year, as I had 2 of my fans on my LRS 350s go out. Obviously, it was overheated in there. So very beneficial. Thank you. Again, I want to say thank you to our sponsors, Boscoyo, and Wired Watts for sponsoring this presentation. Again, if you have any questions, please feel free to reach out to Brian. I'm going to go ahead and stop the recording.